Thanks a lot, Stefan. So thanks to Ulrike for inviting me here. It's very nice to be presenting in real life. I cannot really see the comments on Zoom, but I'm sure Stefan will keep an eye, so just write if there's anything there. All right, so let me get started. As Stefan told you, I have been in Germany until recently, so the work I will show today will mainly be work carried out with the group I had in Munich there. But I'm also currently building up a new group in Aarhus, and we have open position right now, and also there will be next year. All right, so in the title I wrote something about complexity, complex materials, and complex reaction networks. So let me just define what I mean with this. So in heterogeneous catalysis, there are sort of three components that makes things rather complex for us. There's the materials component, metals, oxides, typically in some nanostructured forms. There's the network of reactions that can take place at these materials, even starting from quite some simple gas phase species. We can sometimes have really complex reaction networks and form a range of different products, maybe some we want, some we don't want. And then of course there's also the environment, since real catalysis is typically elevated temperatures and pressures. I guess you all know too well that if you have a lot of oxygen in your reactor, maybe you have an oxide and not a metal as you form. So this is all something to take into account. So I do theoretical or computational modeling, and the workhorse we have there is the density functional theory, which is sort of has a reasonable balance between accuracy and cost. But still, it's quantum mechanics. So if we want to really do design studies, investigate a lot of different materials, for example, we really need something cheaper. And in recent years, we got a new tool. It has been around for some time, but it has really gained popularity in recent years, machine learning. So I will show some examples how we use that to find some descriptors or models that also allow us to predict these at lower cost. So there's sort of two principal ways one could use machine learning. Maybe there are more, but maybe the most well-known is to train an interatomic potential. So this is used a lot if you want to do structural optimization or high temperature molecular dynamics runs. But in catalysis, what we often, or what I like to do is we do some kinetic or thermodynamic models of the reactions, and we want to predict something about the rate of a reaction and the mechanisms or so. And what we typically need there is absorption energies as a sort of basis input. So absorption energy is there in principle just a local minima on such a potential energy surface. So we don't necessarily need to be able to learn a whole potential energy surface, but what I have been working more with is these more direct or coarse-grained models where we directly try to predict only the absorption energies. So whereas in the other one here, you would train on typically geometric features, bond distance, angles. Typically, we don't know the relaxed DFT geometry of a system, because if we knew it, we would also know the DFT energy. So we have to use something else. And we can use atomic properties or bulk properties and connectivity in the system, something that's specific to a surface or site. And we can also use the absorption energies. There's a quite wide range of choices here. Some are more expensive than the others, and that, of course, something to take into account. So these descriptor-based models, they have really been along for a very long time before machine learning. So a very good example in heterogeneous catalysis is the D-band model by Hammer and Nørskov. So sort of correlating absorption energies here of oxygen. So this is, of course, classical example of a descriptor to predict some materials property here, oxygen absorption energy. So later, Nørskov and co-workers also came up with these scaling relations. So here you relate, for example, hydrogenated version of carbon species or oxygen species with their base atomic quantities, carbon or oxygen typically. And these developments have really had huge importance for all this understanding of trends and catalyst screening. In recent years, as I said, machine learning has also come along. So now this is work from Ulysses group, where they also try to predict binding energies, but with somewhat more complex forms. So this is a convolutional neural network. So you have a graph representation, and then it goes into some much more complicated model, but in the end, you're also predicting absorption energies of the system. Just for fun here, sort of the number of DFT data points that such models were trained to, and the number of free parameters you have in the model, and you can see both are increasing a lot. So one thing is that there's been a development in the algorithms, machine learning methods, but another thing is the development in the computer facilities. So nowadays we can sort of routinely get hundreds or thousands of DFT calculations, whereas back in the times, maybe getting just 5 or 10 was a challenge in itself. So in the work, I would like to show, let's see if I can hide this one. In the work, I would like to show here, basically the overall theme is of using machine learning methods to develop structure-activity relationships for catalytic materials. And the way we would typically go about with this is that we start with some DFT data set for something we are interested in. We apply some machine learning methods to find some, can be descriptors or general predictive models that gives us absorption energies. And the idea is then that this should be sufficiently cheap that we can now explore much more complexity. Could be metal alloys, all of the different types of sites you can have there. Another material class we worked on is metal oxides, where you introduce some dopant atoms to also give you some more variability in the sites. And then we can explore different adsorbates or molecules from atoms, and I'll also show some examples up to more complex species. And this then goes into setting up such a microkinetic model, which really models from the gas phase, absorption, desorption to the gas phase, and everything that happens on the surface, diffusion, reactions here. This can be simple rate equations, but I'll also show some examples where we have these more advanced kinetic Monte Carlo simulations. And this can then be used for a single material, but also sometimes more materials to do screening. We can predict something like the rate of a given reaction. But another thing that we can also now compare to more traditional screening studies is that since we can take into account quite a variety or complexity in what are the sites and what are the molecules, we can actually also start capturing like changes in mechanisms. Say, if you have both very noble or very reactive metals, maybe it's not the same mechanism that happens in both. And you can only really know which happens if you can take into account the whole range of possibilities. And another nice aspect is sometimes we can also get some physical insights by then linking this back to these descriptors and to really understand what is it at this level here that controls the reactivity in the end. So let me jump into the first machine learning method that I started working on, which is a compressed sensing method. So this comes from signal processing. And the idea is that you would like to reconstruct a signal, or in general a function, by doing only few samplings or measurements on this function. And the assumption that we make here is that this function is sparse in some basis, so that you can write it in terms of where only a few of these C coefficients here are different from 0. And applied to catalysis, then the problem we are after is how do we find this unknown function here that links we call materials features to the reactivity that we here define as the adsorption energies. And the sampling here is then that we want to preferably use a rather small DFT data set to train or to learn this function here. And this was work we started out in collaboration with Matthias Scheffler and Sergei Levchenko from the Vitava Institute. And we used this method called CISO that they developed. So it applies a symbolic regression to find these Ds here. I'll show you some examples how it works, but it's basically some analytical functions of these materials features here. All right, so what are the features that go into our model? I said we had a quite wide range of choices here. It could be, for example, some key adsorption energies on such a given site here we are interested in. Oxygen or carbon are typically used, but it could also be properties of the materials, like some atomic properties, like electronegativity of an atom here, or some interatomic distances in the bulk material, something we calculate for a given surface or site. There could be a work function, or it could be on a given atom we project, for example, D-band moments onto that atom, electronic properties, connectivity of the site. Of course, if we have such more complex sites here on a metal, then we would typically do an averaging over the atoms that are involved in the active site. This could be one way of doing it. So just an example of a very simple of these analytical functions that we found here. This is for oxides. This is a nickel-doped ruthenium dioxide surface, and this is trying to predict OH at the site here. And you can see it picked out these features as particularly important for this property. So the oxygen adsorption energy, obviously, we know scaling relations exist, but there are also some corrections like the Mulliken electronegativity and some D-band center related properties. And then the idea is that you get out a prediction from CISO, which should hopefully match rather closely the DFT value. Now, in the very first project when we applied this, we were interested in transition metals. So these are more simple in terms of electronic structure and maybe also more well studied. So this was a logical starting point. And here we were specifically interested in, say, if we train our models only on pure metals. So we picked some different ones, and we picked some simple adsorbates we were focusing on in this case. Then how well would we be able to predict such more complex materials like the alloys with these models? And basically what I show you in the plot here is the root mean squared error on the y-axis. So obviously we want to go as low as possible. And then here on the x-axis you have the descriptor dimension. So this is how many of these C coefficients are different from 0. And so we also have something we call the wrong in this method. So this is the symbolic regression. So it takes these primary features and it starts combining them using mathematical operators. So the wrong is how many iterations do we do this? It becomes more and more complex. So here they are all properties of the clean surfaces. So what I plot here in green is the field circles here are the training on the pure metals, and the open circles here are the validation on the alloys. And what we find here in this round 0 here, which is just our set of primary features, is not so surprising. We find that the best single one is the D-band center, which you of course recognize as the D-band model I introduced before. But the idea is then you can start doing these more complex formulas. So example, here's the 2D one. You have also the work function appearing in the second dimension. We have here where we start multiplying them together in rung 1. So here the D-band center multiplied by the filling. Or in this two-dimensional rung 2, you can see it starts becoming a bit more complex functions. You can see something like the density of states at the Fermi level is also picked out as something that's important for the reactivity. You can continue like this, and it gets more and more complex. You can see at some point here, the validation area here on the alloy set will level out, and you will not really get any better. So this is just as an example, how does it look like for this 5-dimensional rung 3 descriptor. It starts getting really complex, maybe not so easy to physically interpret anymore as the D-band center. But what is really nice for applications is that we're actually down at a rather low error, 0.18 eV, which is not so far away from what the uncertainty we typically associate just with DFT itself. So this is basically something we can use for screening. And it's also interesting to note that these 5 descriptors here were picked by the CISO method from around 10 to the 12th possible functions by some clever mathematical tricks. Next, let me show you what we can use this for. So I said we were interested in screening, and here we were particularly interested in one aspect that's sometimes a bit overlooked, which is the active site representation. So how do you represent all of the possibilities for sites you have on the surfaces? So here, this is an example. This is CO methanation at stepped metals, and you can see you have you have some different terrace sites, different step sites, 4-fold coordinated site. And so the state of the art for screening is based on scaling relations. You can see one example of the volcano plot, where you have these descriptors, the carbon and oxygen talking this. And they are really nice for sort of visualizing how different transition metals are located and where there's the top of the volcano is close to where you want to be. But there are also some drawbacks in terms of the efficiency. So you typically need to fit separate relation for every site you want to consider. Also, if you want to use this for screening, you need to actually calculate these adsorption energies, maybe at several different sites, which is, of course, makes it more expensive. So often in these screening studies, you have a highly simplified representation of the sites on the surface. So basically the key advantage, what you can do now with the CISO descriptors, is that we just do one DFT calculation of the surface, and then we can get basically all of our adsorbates and mechanism at all of the possible sites. So the reaction we were interested in is also CO methanation. This is the mechanism that we took from a literature study, starting from CO and hydrogen. You have the CO dissociation that also experiments have confirmed that this mainly happens at the steps. You have the hydrogenation steps, carbon and OH. And basically the question that we ask is like, what are the active sites to focus on here? Especially when you go to an alloy, then the complexity is even worse. So to sort of assess what does it mean in practice, the choices that you make here, we compared some different models. So what I call reductionist is simply you take nickel, the industrial catalyst, you take the most stable site there, and then you always use that in your screening. Or you could do a little bit more, the one we call simple, a little bit more advanced. You say maybe something like OH, it could sit not only at the step sites where it's most stable, but maybe also on the terrace site. But you take into account just one site within each group. Or you can do the most complex models where you say all of the adsorbates in principle sit on all of these site types, And for every site group here, we look into all of the possibilities to find the most stable adsorption site and basically cover everything. So this in principle means that you then cover more possibilities for how your reaction happens on the material. Just a little bit about the microkinetic models that we use. So we use rate constants from transition state theory. I said we were always predicting these adsorption images. Of course, we also need the barriers to go into these, and these we get from these Brønsted-Evans-Polanyi relations. So from the adsorption images, you have the reaction energy, and then you can predict also activation images. And for the screening here, we typically rely on this mean field approximation, which is basically boils down to some rate equations we can quite easily solve. It's rather efficient, but there are some things that we neglect. Typically, we neglect also lateral interactions between the species. But we also do some work on these more advanced kinetic Monte Carlo models, where we can do for lateral interactions through cluster expansion methods, because in these methods you have the explicit lattice. You solve this type of master equation, and you know in every step of your simulation what is the exact spatial distribution of your adsorbates. Drawback is it's for screening, the computational cost is just at the moment rather high. But let me come back to the screening we did here, which was just this mean field approximation rate equations. And I said that now the aspect that we can really do in a lot more detail here is this active site representation. This was work by PhD student Martin Daimer. So the result of the screening is shown in this parity plot here. And here I have the turnover frequency of this most complex model that we could only build because we have all the cheap energetics now. Some standard temperatures and pressures. And on the y-axis here, I have these reductionist and simple models. So you can see that basically the uncertainty that's related to how complete a representation of the site you have, that's huge. That can give you something like 5-10 orders of magnitude on this log scale here. You can see nickel is up here as one of the good, well-known catalysts. You of course want to be out here. There are also some materials which came out as really promising, like iron palladium or iron platinum layered alloys, that came out really good when you take in this full detail into account, but which would be completely missed in the more traditional approaches. So basically this is hugely important as a comparison. The sort of approximate, we know that DFT is also approximate, but that would typically give us something like 2 orders of magnitude on this scale here. So basically the take-home message of this study was that with these new methods, we don't really have to compromise on how well we represent all of these sites at the surface. We can do the full complexity now. Yeah, so this was one example on the alloys, but we also did one project on transition metal oxides. With Wenbin Su, another PhD student in Munich. So here we were looking into oxygen-rich facets of ruthenium dioxide and uranium dioxide, and we doped them with a range of different transition metals. And here we also assembled a DFT data set with the oxygen OH and OOH at the cost sides of these facets here. So sort of, again, standard screening is based on scaling relations typically. So here are the scaling relations for this data set. You can see the trends are there, but in these systems there's a lot of scatter and a lot of outliers. The root mean squared error is something like 0.27 approximately. So this is not quite where you typically would like to be in screening. So the screening we did here, we were interested in electrocatalytic oxygen evolution reaction. So this is this mechanism where you have liquid water that and you produce protons and electrons. At least this is the mechanism we focused on, and we are basically concentrating on these 3 adsorbates here, since these are the ones that bind to the catalyst surface. So as I said, in scaling relations, you would have this kind of linear relation, for example, with oxygen as a descriptor. We then again applied our CISO machinery to look for some more accurate relations here. And one of the formulas that we came out with was what we call sort of a refined scaling relation. So we still have the oxygen adsorption energy in there, but we have also some materials properties to sort of act as corrections here. The Mulliken electronegativity typically came out in many of these formulas as sort of a key correction term to this oxygen adsorption energy here. So what does that mean for a screening study? So in this case, this is electrocatalysis. So what I have here predicting here on the x-axis is the overpotential, and this we get from a thermodynamical model known as the computational hydrogen electrode, originally developed in the NERSCO group. So it's basically the overpotential to make this reaction run, and we would like to be out here around 0, ideally. And you can see the model. This is based on just the DFT energies of these 3 species. And this is when you use the models, the overpotential up here. So you can see we basically, with the red points here, which are these refined relations, we do get a lot closer to the ideal diagonal here than the standard scaling relations. So one of the top catalysts that came out was this iron doped ruthenium dioxide surface. I think there are also experiments that confirm that this worked quite well. But sort of our physical interpretation of why these refined scaling relations are somewhat better at capturing this, it could be related to the fact that these it points out that this electronegativity as something important, which when you think about it, sort of the ability of such a dopant atom here to donate or accept charge is well known to be important in oxide catalysis. So at least you can sort of try to rationalize why this physical formula makes somewhat sense. And it improves on the accuracy of the screening. All right. This was what I had on the oxides. So in the last example here, I want to cover, I want to move one step in complexity, not in the material side, but in the types of adsorbates, so the reaction network that we consider. And so what I showed you up till now was still quite simple mechanisms, very simple adsorbates, maybe an atom or CH or CO, something like this. But there are also reaction mechanisms with much more complex species. So I showed you before the CO methylation pathway, where you basically go down in this way here. But what's much more interesting is if you could start making these carbon-carbon couplings on the surface, you get something like Z-aldehyde or ethanol, which are much more valuable products. So in this work, we focused only on one metal, rhodium, the 211 and the 111 facet, and we could do these much more detailed kinetic Monte Carlo simulations. We also took into account when the species sits here on the surface. Typically, you have high coverages, so it interacts with the species at the neighboring sites, and that actually turned out to be really important for the reactivity predictions, especially for this 111 facet here. I don't have time to cover all of the details of this study, but basically we obtained a new understanding of some recent experimental results. So there are some results from this paper here from last year, where they synthesized such rhodium nanoparticles of different sizes, and they saw that the larger ones, which you would expect to have the 111 facet mostly, that they were selective to methane. And that was in good agreement with what we found in the KMC model. But actually, in previous rate equation models, they were found to be selective to acetaldehyde. And we think this is maybe because the interactions are so important in this system, and you can do this more detailed with these cluster expansion methods in kinetic Monte Carlo. I also said that typically methane is not really what we are interested in. We would maybe rather optimize the catalyst to rather produce acetaldehyde or ethanol. There are also some experimental works on this, such as the doping the rhodium with iron or manganese, or maybe an alloy, which is cobalt copper alloys. And of course, if we want to go in that direction, then we cannot do everything based on DFT like we did here. We need a machine learning model that can actually predict all of these complex species here. So in the last time here, let me just focus on such a work. This is work by Wenbin Su again. So he developed indeed such a machine learning model for these more complex molecules. And you can see that the main challenge for these, this is hydrogen, carbon, carbon, and oxygen. When you have such a species on the surface, it can take quite a lot of different adsorption motifs on the surface. It could bind through just one carbon like this, or maybe through both of the carbons, or maybe also through the oxygen. And if you also have an alloy, here you can see there's a lot of possibilities to go through to find the most stable motif. So we want to be able to predict this with machine learning. And to do that, we also need some new features or input that takes into account also some geometry information of the adsorbate here. We don't have the full DFT relaxed geometry, of course, because if we had it, we would also know the energy. But what we can use is a graph representation. So basically putting the molecule on the surface in a certain motif, and then counting, in the graph here, the atoms are the nodes, and then the way the bonding is represented with these edges in the graph. So this is something we can use that we have available. And as a machine learning method here, we focused on Gaussian process regression. So it's a supervised machine learning technique. It's the same as with the CISO, that you have some DFT data. You need to sort of fit a function to it, or find a function. Here we are not, it's not an analytical function, but we learn basically a probability distribution over possible values this function could take. And what we also have in GPR models is that we have this, we have both predictions of the model from the mean of this distribution, but then we have also error estimates from, example, from the standard distribution of this, which can come in quite handy if you want to do something like active learning, where you really need these. I'll show an example of this later. Of course, the key thing about these models is also you have these kernel functions that take two data points and basically measure how similar they are. So here's an outline of this model that we developed. So as I said, we have as an input here the optimized geometries of the gas molecule and the clean surface, and then we can put the molecule in some adsorption motif. We have this graph representation of the motif, and we can now use similar features as we did in the CISO models I showed you before, but we can use a feature vector for every atom in the graph here as what you call node attributes. So you can take into account, for example, the dependent of this surface atom and this one, and so separately, which you could not before. And all this is fed into a GPR model. As I said, we need a kernel function, and since we're working with graphs now, we are using a graph kernel. It's called the Wasserstein-Weisfeier-Lehmann kernel that comes from this paper here. I don't want to go into all of the details, but it's basically a function that takes two graphs and then gives out a number how similar or not they are. And we also customize this a little bit with some additional hyperparameters. So basically we have some physical intuition that probably the atoms that are here right at the interface between the molecule and the surface are more important, should have a higher weight than those down in the bottom. So these are some hyperparameters that the model learns itself while we are training it. So how well does it work then? So to basically show why we need this graph representation, let me compare here the results from two types of machine learning models. So one is where we use this vector form of the input, like I showed you before. So you can have some global features, like for example of the molecule, the LUMO level of the molecule, or you can do some averages over some atoms in the system. You can also do this with GPR, just with a standard radial basis function kernel. And the other is then where you have the graph representation. So you can have features that are specific for every atom in your graph. Yeah. And the way we compare how well do they do is we have some DFT data set we call a 5-fold cross-validation. So basically we split up our data, we train on 80% of the data and predict on the 20%, and we repeat this. And then we quantify the root mean squared error over this combined test data set that contains one data point exactly once, each of the data points exactly once here. So how does that work? First of all, let me show you for the very simple ADSORBATES that I also showed you results for before. The new thing compared to what I showed you with the CISO method before is that we have these ADSORBATE specific features, so we are looking for just one model. And this is basically the reason why for CISO it doesn't work that well. There's some scatter root mean squared error of 0.24. The GPR models, on the other hand, both work extremely well for these simple species, 0.13 EV for both of them. So basically for the simple species, we don't really need this graph representation. It doesn't make any difference. But when we now move to the more complex ADSORBATES, so here we have a new database. So we have 41 different, from atoms to very complex species. We did this on 4 different transition metals, copper, rhodium, palladium, cobalt, 2 different facets. And you can see that now in the 2 GPR models, the graph representation works really well. 0.18 V in root mean squared error, so similar to what we could do before for the simple ADSORBATES. But without it, it does not really work, which is maybe not so surprising when you think about it. Let me just show you one example where we look at these test errors just for one of the molecules, CHCO on one surface, the stepped copper surface. So you can see you have here A, B, C, D, E, F, G. You have all of these different absorption motifs on the surface. The green points here are the DFT images, and the red this graph model. So you can see here you can really capture all of this, these different motifs and how stable they are with respect to each other. But when you don't have this graph representation just in the vector-based model, the black points here, then it just predicts more or less the same absorption energy. We cannot really distinguish how it binds to the surface or not. So this is the main reason we need the graph. And the good thing is that we can get this accuracy that is also, again, actually really useful to do screening. So in the future, what we think we can use this for is, as I said, active learning. So the idea is you want to start with some preferably rather small database, like the one I just showed you, something like 1,000, 2,000 data points. Set up this model on this initial system, start applying it, maybe predicting some new materials. It could be for ethanol synthesis applications, for example. And then you have these uncertainty estimates. You can then say, okay, maybe the model is really uncertain about this data point. Maybe I want to actually refine it. Or you could also do a full kinetic model, sensitivity analysis, find the rate determining steps and see, okay, this step is really important for some promising material. Maybe I also want to refine that one. And then you do some new DFT calculations and build up this way. So that the model is basically itself really focusing on becoming better at what you really need it for. So the idea is to have this all happen in some automated workflow. CO2 hydrogenation is another reaction we are quite interested in. So yeah, with this I reached the end of the talk. Let me just sum up what I covered today. So I started out with this CISO method to find descriptors. So these are analytical functions for the talking use. And I showed you the different types of materials and active site motifs we could cover, like alloys and oxides. And the really nice thing here is that since it's an analytical function, you can start interpreting really look at the ingredients that go into it. For the more complex molecules, we need this graph representation. We need some more complex machine learning model. I showed you that we can get just one model that works simultaneously for a lot of different molecules and materials. It's less interpretable, but we do have some physics in there also in these node attributes we use. And then I showed you a few screening examples here. So one thing we can do now is that we can have these rather complex kinetic models where we take into account all of these sites at the surface. And in the future, we want to go towards these active learning applications. And with this, let me just thank the people that were involved in this work. So co-workers in Munich, now in Berlin, students that worked on these projects. Also thank the people that joined my new group in Aarhus, Compute Time and funding. And thanks for your attention.